Good morning, everyone. I'm David Bühler. Sorry for my voice. I will talk about ALTIUS, this time about the system characteristics and performances. This will be mainly focused on L1 and some of the key requirements that we have to meet, and therefore also then our challenges and the ways we have tried to meet those requirements. We've already had some talks, especially from the in-flight calibration, and those feed directly into what I will present. So let's get started. So you have basically seen the slide already from Daniel's talk. We take 2D images in the UV, vis, and near, and you can see these spectra at the top. These are basically the two standard inputs that we have at the system level, at L1 level, that we use, and you can see them at how the spectrum varies at various altitudes, and of course we are in a limb geometry, which has been explained many times by now. So we look at the bright limb, and we also have occultation mode of the sun, bright limb, planets, and also the moon. We have a field of view of about 100 by 100 kilometers, or about 2 degrees. But of course, the great thing about this platform is its agility and to image and many different objects. So this is another slide that will be already familiar to you. These are the instruments. You can see a sort of a diagram at the top right, or the real copy here. We have basically these instruments are stacked on top of each other. The vis and near are both acousto-optical tunable filters. And then we have a stacked Fabry-Perot for the UV, and you can see sort of a schematic optical diagram here at the bottom. What is missing in this diagram are a few bandpass filters that are basically further used to block the sort of out-of-band light that of course will enter the main aperture. In the UV we have an extra aperture in order to increase the SNR during occultation mode. And another key component which has not been drawn in here is that we have a switching mechanism. In the UV you can see it to switch between the two apertures, but we also have a neutral density filter in these switching mechanisms, so that will allow us to observe the sun, as you know. And we have basically 3 separate detectors, but they're all basically the same CMOS detector. In the UV, the top filter layers have been taken off, so that the silicon detector is also sensitive in the UV. And depending on the observation program that is then selected, we can select anything within this wavelength range for each of these channels. So here's some illustrations of the spectral performance. So on the top left you have the UV centered at 350 nanometer, and one of the characteristics of this Fabry-Perot is that you have some side lobes. One example is here. This is in actually the worst case scenario. This is based on simulated data of the actual instrument, and which is currently the engineering models being tested right now. And so you have to take these extra lobes into account. That is mainly an issue for stellar occultation. In bright limb, this is less of an issue due to the evolution of the spectrum as you look through the atmosphere. This is less of an issue for the ALTIUS. You can see the typical sync function there, and they are generally more behaved, but of course they will also show some slight asymmetries based on past experience and based on the simulations that are available to us right now. And on these graphs on the very right, you can see the typical full width half maximum values that have been simulated for all of these instruments. And in the UV, you can see also the requirements that we have. So in general, we try to be below 4 nanometer, and in general we do meet that, except for the longest wavelengths where we will tip slightly over. In the AOTFs, I have not drawn in the requirements. The requirements are set in wave number, given that it is an AOTF. So if you convert this into nanometers, you will naturally get a broadening as you go to longer wavelengths. We do, in general, meet the requirements, but again, in the last quarter of the spectral range, we are above the requirements that are set by the SRD. In general, we have a very good spectral registration. So compared to the full width of maximum, it's only a small fraction. But as you know, we also have in-flight calibration of the central wavelength position that we will do in flight in order to inform us about the SRF. So this is the general overview of the prototype ground processor as we have it right now. We have several L1 levels and of course L0. We do a few things on board already. So when we take a single image, we automatically apply a bad pixel correction. This map can be updated, but of course it is applied already on board, and so it is difficult to undo if you have errors. So this is something that we will definitely have to calibrate and evaluate on a regular basis. Then we also do some onboard binning. This is usually 3x3 in order to improve the data rate. And so therefore you have the native pixel size of the sensor, but also you have what we call science pixels. And then this data arrives on ground, where it is then transformed into what we call level 0 data, where the data then becomes an image as you would know it, with some metadata from the platform. And then the correction process starts, and these are the levels L1A to C. Now, we have generally quite standard corrections, as would be expected. So we have a photo response nonlinearity. We take care of dark currents. One special thing about the AOTFs is that you have a zero-order correction. So this is taken at every observation. You will have an extra image where you basically turn off the AOTF, which is then an image which contains both the dark current non-uniformities, but also any scattering due to the AOTF, which can then be subtracted from the actual observations. This is again a very standard process. And then of course we have the photo response non-uniformity map, which again we will recalibrate in flight. L1B is then trying to assign altitudes to all the pixels using the geometric calibration. And then finally, the most interesting part, maybe the most novel, let's say, is at L1C, where we will try to correct for stray light, which is a particular issue, of course, in the bright limb, not so much for the occultation observations. And then finally, we will do a final binning of these science pixels down to only in the bright limb to 5 columns. So then you have basically a vertical resolution of 1 kilometer by pixel size and 20 kilometers in horizontal. And we do this in order to meet the SNR requirements. But of course, this is an adjustable parameter and can be adjusted as needed. Another word on the stray light correction. So what you see here are these simulated PSFs, as best as we know them from the instrument. On the visible, and here in the UV has a special thing that we have some ghosting due to the Fabry-Perot, so there's some extra light that bounces in between the Fabry-Perot stacks. To deal with this, we have basically angled them slightly in order to make sure that these ghosts fall outside the field of view. And what you see here is these detectors actually cover a larger field of view than what we will actually read out during science data. So these ghosts that you see are usually not observed. At least the main lobes of them are not usually observed. But as has been highlighted, we have what is called Earth shine. So we have a very bright Earth, which is brighter than the actual observations in bright limb, which means that especially the higher altitudes are contaminated by stray light. And this is stray light that is really due to the scattering properties of the individual optical elements. And that's why we have this enormous PSF. Over several degrees, effectively, that we need to know, that we will measure on ground, but that we will also try to recover in flight with the processor that has been outlined already. And in there, we then basically this PSF can be fitted by Harvey functions, so we can extend it if needed. And then we can use this PSF in order to recover the true spectrum, and that an illustration of this is provided on the top right. So what you would see in L0 is this green line, and then after the correction you will get to this red and black line, and you can see here that we use a combination of this extended PSF in order to perform a deconvolution, and then we use this top part in order to estimate the radiance coming from the ground. And what we can see in the scenes that we have available to us at the moment, the simulated scenes, this methodology works well, but time will tell. This is an overview of the in-flight calibration processes. You've seen the ones developed by USASC. We also have some other ones that are developed by Redwire, who are also doing the performance model. So we have a geometric calibration for the L1B. We also have some dark current and dark current non-uniformity, especially for the UV, that will measure the bad pixel map that I've already mentioned, and of course the photo response and non-linearity of each pixel. Here's some expected outputs, some sample images. Top one is the UV, and bottom one is the one in the visible. You can see some residual influence of the ghost in the UV, and that is then removed by the time you get to L1C after the deconvolution. In the visible, of course, we do not really have ghosting, so but what you see very much at the L0 level is the effect of the peer renew that has these undulations that are typical for an AOTF, but by L1A this has typically been corrected, and the better your knowledge, the better the correction, of course. This is what you would see when you look at the star. I've had two positions in the atmosphere. This is a bit like finding Waldo. So usually the star is in the center of the image, but then as the star sinks through the atmosphere, it starts to drift upwards. So you have to do peer renew corrections and dark corrections because you basically see the star over several pixels. So you have to take this into account. In this case, at the moment, we will not do binning of the data, so not even onboard binning. So it will be the native resolution of the sensor, but we will window the observation. So we only read out a subset of the pixels in order to retain the data rate or the frame rate, so to say. Another example, solar occultation. You can see here the sun slowly drifting. Again, similar general behavior as with the star. We will apply the general processing here as well. We have a discussion at the moment whether at L1C we should also apply a deconvolution in order to improve the image and reduce the stray light of the sun. But we have an algorithm that is being developed, but of course we can adjust the processing pipeline as needed. Here's some quick overview. When you apply the best knowledge of the instrument that we have with the scenes that we know, in an ideal sense, we can see, okay, under these ideal conditions, where are we with respect to the requirements that we have been set? Here are three examples in the UV, visible, and from the near channel. And these triangles are basically the requirements that we need to meet. And the green line is then the final binned L1C product. And you can see we generally meet the requirements and SNR. In the UV, it's a little bit tricky, and these black lines are essentially the L1B and L0 unbinned precursor product, so to say, and so you can see why we really need to bin. Stray light, again, this is related to the bright limb PSF deconvolution. You can see before deconvolution, we have this black line, which is the requirements that we have been set. So generally less than 1% of the signal should be stray light. That's in general the requirement. And without a deconvolution, we do not meet that, despite the baffling and the field stops that we have within the instrument. We then need to also do post-processing. And as you can see in this ideal scenario, we do manage to get below the requirements that we have been set. And in general, across all the wavelengths for which we have requirements, only some in the visible around 500 near the upper end around 50 to 60 kilometers, we struggle a little bit. Stellar occultation, SNR, that is maybe the biggest issue at the moment, is that in the UV we generally manage to meet the SNR requirements, but in the visible and in the near we really struggle, except for Sirius, which is the brightest star, as you know. But for dimmer stars, we do really struggle with the nominal exposure time that we have been set in by the requirements. But of course, in stellar occultation, we have some issues that we need to accept, which will limit the number of stellar occultations that we can do in a typical orbit. But of course, solar occultations do not suffer from that problem, as you might expect. Stray light. The stray light in stellar occultation is mainly dominated by the out-of-band components, and that is in particular an issue in the UV. You can see the out-of-band stray light in these top 3 right bands, and generally they're below the requirements. A particular thing about ALTIUS is that out-of-band and spatial stray light are considered the same, or they have to meet the same requirement, and so. But in general, the out-of-band stray light is not a concern, and in the visible, it's really not a concern. So and in the solar occultations, neither. So to conclude, we'll have a typical observations. An observation consists of several individual images, a whole set of images. In fact, we will have 131 in the bright limb. 2 solar occultations, obviously, and then we aim for 5 stellar occultations, likely going to be less. Spectrally, we typically are below 4 nanometer in full width half maximum, but towards the longer end of each channel, we are generally above that. The secondary lobes in the UV will have to be taken into account. We will try our best in the on-ground calibration, but of course what we can do in orbit will be far more challenging in that respect. SNR, generally compliant, but the stellar occultation is in the visible and near channel is an issue with respect to the requirements, of course, which are around 100 SNR typically. And then finally, the stray light, we have a working method that seems to work with under these ideal conditions that we've been testing them. And now we will start to expand this by simulating the on-ground calibration, the in-flight calibration, so errors in the PSF, and then also we will introduce some more challenging scenes that is mainly done at BISA using the end-to-end simulator to see whether that will give a different picture on the stray light situation. So that's all that I have. Thank you very much.